Okay, we are back. It is Tuesday on a Friday day, right? November 24th, couple days before Thanksgiving here. Chapter 14, we're still in the middle of it. Splitting will be the main topic today, although we've already talked about the N+1 rule. We've given you all the fundamentals, but we're kind of progressively getting more difficult in our analysis. So you'll see a progression here, and problem solving is the goal, to get to the point where we can solve structures, propose a structure that's consistent with all the data. And that's the goal here. Quiz 8 is due today. Hopefully you're already looking at that. I've helped out a couple people with that. You've got to make some assignments there. And the number of sets of compounds, the topicity thing is there also. And then homework 14 won't be due till next Monday. And we will have next Monday after Thanksgiving, which is now all online. Sorry, this is our last day for in class. Sorry about that. We'll be online. We'll be shooting the videos in similar way, though, at the same times. So the TAs and I will be kind of lonely the last couple weeks, but you'll have, be able to look at the videos. You'll still be able to zoom in for office hours and recitations. So that's not going away, okay? It's just class that'll be online. And quiz 9 will be posted on Learning Suite sometime this weekend. Don't let it ruin your Thanksgiving weekend. But if you want to get a head start on it, it should show up on Learning Suite soon. Yeah, so keep an eye out for quiz 9, which will be coming up there. All right, we left off last time going through the different shift values here. And don't memorize these. There'll be a data sheet for test 4 and the final, so you'll be able to see the shifts for different groups. You have to be able to use these to solve structures, okay? But you should understand why different signals are where they are, right? Based on electronegativity, proximity to those electronegative groups. What was the other key factor? Hybridization, okay? And now diamagnetic anisotropy, which we're getting to. So I left off with this last time, and I told you I wanted to go to the board to try to draw through this to convince you why this is an important thing. So, aromatic carbons here, like in benzene, and I got the model here too, benzene, C6H6, right? It's got these conjugated pi electrons. There's 6 of them, okay? It's a flat molecule. All the atoms are flat because of the hybridization here. And the unusual thing is here, the delta value is in the 7 to 8 range, ppm wise. Why is that so far downfield, so far de-shielded? Well, it has to do with how these hydrogens on the side, and I'm only drawing a couple of them here, are exposed to the external magnetic field, okay? And let's see, so these are pi electrons, so it actually creates an electrical field here, okay? And as these electrons can move around, we can say, that's a current. It's a little mini electrical field created by the ring current of these electrons as they move around. Now they move around in such a way that it's what? In the plane of the aromatic system. Well, perpendicular to this is a little magnetic field that's created here, okay, that has field lines associated with it. Now this is the magnetic part of this. I'll use mu, which is a symbol for magnetic moment, if you will. And these field lines are actually perpendicular. It's like toroidal. It's donut shaped. So this is just one two-dimensional cutout of it. But you can imagine a whole donut here going around top and bottom. Wow, my art's getting very messy. Sorry. So there's 2 fields there. The electrical field, which is in the ring, okay? And then perpendicular to it is the donut, okay? And that field lines up in such a way that it tries to oppose the magnetic field of the large magnet, okay? So these aromatic rings line up in solution in such a way that the induced ring current here creates this extra magnetic field that opposes overall, the total thing here opposes the magnetic field of that. So you can see the direction of these lines are coming down there. But what it means here is the direction of these lines on the outside are what? Pointing up. And on the exterior, they're actually adding to the magnetic field that the molecule is seeing overall. Here they're subtracting from it. It's going down. These are coming down this way, the direction of it. And that's what anisotropy means. It means directional thing. So in three-dimensional space, this induced magnetic field is not the same in all places in 3D space. On the periphery of an aromatic substance, we see strong deshielding. In the interior, though, if you could have an atom hanging over the top or the bottom of an aromatic thing, it will actually subtract from the magnetic field because it's trying to oppose it. Okay, so this is called the shielding region, top and bottom. Okay. But that's not where the hydrogens on the periphery are. They're in the deshielding part. Okay, where they're feeling an extra magnetic field. You see. Hydrogen outside. And it's all 6 of them in the case of benzene. So it resonates a little bit higher than you expect just for the hybridization. Okay. We saw with alkenes, sp2 hybridized, or what, in the 5 ppm range. But then to get up 7 or 8, we have this added effect of the extra magnetic field induced by the ring current, which in an aromatic ring, can be substantial that way. Okay, with 6 pi electrons. We'll learn a lot more about aromaticity in 352. Very common in all sorts of things, including amino acids, phenylalanine. You may have heard of benzene there. Now, alkenes, hybridization's the main thing, but you can think of this as a little mini ring current also. You only have 2 pi electrons with an alkene, but you also have this little ring current. It's not as strong as with benzene, but then you have it opposing the magnetic field. And on the periphery, these hydrogens here feel that extra additive magnetic field. Okay, so they're shifted in this 5 ppm range. Okay, alkynes are the strange guys. and you might say, well, these are sp hybridized now. Okay, so yeah, these would be even higher. 10 we've kind of proposed. Okay, more s character here. Okay, but actually the induced magnetic moment is going to have a different geometric disposition, such that sp terminal ones will actually have a shielding effect in addition to the hybridization effect, and they're actually moved upfield to around 2.5 ppm. They're the outlier, and don't worry about that. It's kind of a funny effect. Let me show you that on the board. We'll go back up here, Joshua. So there's a field. You don't see everything fully discussed there, but you can see on the side here, these are the ones that feel the extra magnetic field. And these orange lines here are the magnetic field. The black thing is the ring current for the electrical field. Okay. Electricity, electrical fields, and magnetic fields are always together in electromagnetic radiation, right? They're perpendicular to each other, okay, which is a neat thing, physics-wise. But here's alkenes. You can consider them the same way as the aromatic things on the periphery. They feel this extra field. But now with alkynes, actually the electrical field goes around this way because the 2 pi bonds are perpendicular to each other, 90 degrees to each other. So it switches the direction of the electrical field, actually. It's going around here, like my cursor is. And that induces the magnetic field this way, where the hydrogens on the end actually feel a subtraction of the magnetic field, the applied magnetic field. Okay, so that's why they're shifted further, upfield at 2.5, okay? It has to do with this anisotropy effect. In 3-dimensional space, these extra magnetic fields are a little different compared to alkenes and aromatics to alkynes, okay? We might expect this to be very high, but it's not, okay? It's mitigated. We have this extra shielding effect because of the different anisotropy here, the array in 3D space. But yeah, don't sweat that. It's just a thing. Keep track of that. Alkynes will be on the data sheet. You'll see where it is. Yeah, there it is. Okay, so this is the whole thing with the pi electrons. Yeah. Okay. Questions on that? Yeah. No, don't worry too much about that. Just know how to use it and keep that in mind. So here's what we're looking at, right? All the different shifts that are involved there. It's a pretty wide window. 0 to 10 is typical, but if you have aromatic or aldehydes, these can be up here around 12. Okay. Hydrogen bonding with carboxylic acids and with alcohols. Alcohols aren't on here. No. Okay. We'll talk about that again. With hydrogen bonding, it can be variable depending on the concentration, and no splitting to hydrogen. So we talked about this before, integration. This molecule we actually looked at before, terbutyl methyl ether. And so here's the whole thing. These are both singlets. There's no neighbors here. So just two sets, two signals. The terbutyl is just one. And then the methoxy methyl there is shifted downfield at 3. Why is it at 3? Question. Why is this one up at 1? What's the key factor there? And in fact, this is the key idea you'll see over and over again. Why is this methyl up at 3 and this one down at 1? Anyone help us out? Remind us of that effect? Yes. Deshielding due to the proximity to the oxygen. Yeah, the electronegativity. Okay, that's going to perturb the electrical field there and leave these hydrogens more exposed to the external magnetic field. And it's shifted further downfield. What about the integration here? 60, 30. Now, these are random numbers sometimes used by the computer, and they'll just be generated in there when it does a separate experiment to integrate the area under these signals. They don't just like sharp lines right now, but if you blow this up, you'll see a little bit of area under each peak. That can be integrated, separate experiment. Computer often will just assign an arbitrary number. Oftentimes what you do is just take the lowest integral and divide it by the higher one, and you'll get the ratio. And what would that be? 3 to 1, right? Now that's just the ratio. Sometimes you have to think, well, my smallest one isn't just one hydrogen in the structure, it's actually 3 hydrogens. So the true ratio is what? 9 to 3, okay? But these numbers can be different. It might be 51, 17, whatever. And it might not always be exact. You'll have to kind of fudge around with it sometime. So here's one, a little bit different for the integration. You see up here at 7, you see kind of a broken up. It's not a real symmetric line. You can see some definite area under that one. And you got 54, and then you got something at 5, and something at 2. And this 54, 23, 33, what are you going to do there? Okay, well, you can divide by 10 maybe each one of these. So what would you get? 5 to 2 to 3? And that might make some sense to try to figure out the structure. But when you see 5 up here in the aromatic, what is that? That's probably a monosubstituted benzene, okay? So let's try to do this one. So look at that one there. Let me give you a little more data on this. And when we solve problems, we always give you more data, right? So for this problem, and we'll go back to the spectrum and look at it here in a second, C9H10O2. So I'll give you that. So our assumption there that there were 10 aromatic ones and then 2 and 5 makes sense here, okay? We can see we got 3 sets. They're different. And they're what? It's 7.3. That's the one with 5H. And then we've got 5.1. That's the one with 2H. So I'm doing the integration for you here. We divided by 10. And it wasn't exact, but that gives us a feel for what? The ratio of how many hydrogens are in that signal, right? And then 2.1, 3H, okay? So what are we gonna do here for this? Oh, IR, IR, 1710, inverse centimeter, okay? So what do we probably have here? 1710, that tells you what? You have what right away? Go back to chapter 13. 1700, what is that? What functional group? OH, an alcohol is 3500, but if something involves oxygen, what is it? Carbon, doubly bonded oxygen, what do we call that? Carbonyl group, okay? But that can be a lot of different things. So we kind of have to look at this and say, well, these might be alpha to that carbonyl, or it might be on an oxygen. This is pretty high up here, okay? This 5.1. If it's just alpha to oxygen, that'll be about 3.5, okay? So this one might be next door to a benzene and maybe an oxygen, okay? Whereas this one, 2.1, that's alpha to the carbonyl. And this 3 here, and they're all singlets, by the way, so they don't have any neighbors. Well, the aromatic one, we need to talk about that. if you have a monosubstituted benzene, actually they do have neighbors, but they all have very similar shifts. So they're all on top of each other. They don't split each other, but it's kind of a messy looking singlet. Okay, so that's why I drew a messy looking S right there. Yeah, okay, but let's piece it together. Okay, we've got a benzene. So we got that structure. And we got two oxygens. So what do we probably have with a carbonyl here? And right, no OH, no alcohol. So we don't have a free OH. So what functional group might we have? Let's add another oxygen. And so what would that be? A what? An ester, right? And look, if we think it's an ester, this one right here, 3 H's, it's a singlet, that's perfect. That's alpha to the carbonyl, and that's just where those come, 2.5, 2 or so, okay? It's an alkyl methyl group, but because it's alpha to this electron withdrawing group, the electronegative oxygen, but it's not right on an oxygen, okay? That might be this one here. And so that's kind of what's in the middle here. What do we have left? 2H here, so that's probably a methylene with something on it. So just by analyzing the fragments, can we propose a structure for this spectrum? Yeah, I think we can. Benzene, let's just stitch them together. Oftentimes we get to the point where, okay, this one can accommodate two groups. This one is kind of on the end here and we're done, right? So let's stitch it in there. Let's put this methylene right here. Oh, right there, okay? That actually turns out to be the correct structure. Okay, now I kind of jumped ahead and just launched into that. But there are some other ways we could array these and begin to think about that. What about this? If we had this, and then we put the carbonyl there and the methyl group there, okay? That would be the same formula, but would it be the same shifts? Let's see. If that's alpha to this oxygen here, that shouldn't be at 2.1, which is where that is, 2.1. If this is alpha to this oxygen directly, this should be up at 3.5 to 4, okay? So you can kind of rule this one out. This one would get partial credit, but it's not fully consistent with all the data, okay? And that's where you get to when you start solving some of these problems. Look at all the data and begin to piece things together. And this is a relatively simple one with no couplings. We'll use the J values and the couplings, the N+1 rule, to help us out. But you can see here just the pieces and the shifts and the number of hydrogens really lead us to this molecule right here. Okay. There's some others you could propose, but they wouldn't be fully consistent with that data. Let's go back and look at that data right there and see. Yeah, okay. So yeah, I think that's consistent with that. Okay. Yeah, and this is kind of a messy looking singlet there, but it integrates for 5. That's the 5 to 2 to 3. And we're given the formula, the ratio of atoms, so we can confirm that. And then the shift here being far downfield, alpha to that oxygen and next door to the benzene. So this feels two things that are shifting it downfield, the oxygen that's alpha 2 and the aromatic benzene, okay? Whereas this one's more alkyl, it's alpha to the carbonyl on the other side of the ester, okay? So that's the way to look at it. And that's a fine thing. All right, let's get into splitting now on the board here, Josh. So we've shown you splitting before. We introduced the N+1 rule, and you saw the splitting for ethanol when we talked about a little of the history when Bloch and Purcell built the spectrometer. They sent the grad student over to the stockroom, hey, give me something with hydrogen in it, and they wound up with ethanol. And saw the 3 different signals. They got things tuned up well, and they could see the splitting. Okay, and that N+1 comes out of quantum mechanics, and we'll just show you qualitatively how that goes. Let's look at this molecule and think about the splitting patterns here. So we've got this hydrogen right here, and then we've got these 2 hydrogens right here. Okay, so tribromoethane. Let's look at the signal for this and analyze what's going on here. This one will be at 5.7 delta. This one, or these 2 are the same. They'll be at 4 delta. or ppm. This one will show up as a triplet. We need to figure that out. These two, okay, integrating for 2, will show up as a doublet. Okay. So how does this work? Let's see. Let's analyze. Let's see. Yeah, let's do these two first. The doublet right here at at 4. Seeing with one neighbor, showing it as a doublet. Now, how does this work? Now, if you could think of that signal right here at 4 ppm, let's start out initially thinking about it as a singlet. Okay? But you know, the shift in the magnetic field and everything are going to be changed because of the hydrogens right here, its neighbor, okay? So this one in the triangle here has spin states also. So we're observing these right here, okay? There's 2 of them, right? And what this sees here is the magnetic field, and it sees the little magnet from this, okay? There's a little magnetic moment there as that nuclei spins, okay? Now, what are the spin states of the nuclei? Plus 1/2, okay, and minus 1/2. Well, that spinning then can either add to the magnetic field or subtract from it. Okay? They're small. This value is only about this difference here in this we call the J splitting, and it's about 7 hertz. Now, that's not much out of the millions of hertz numbers that we have for the spectrometer. Remember, these are megahertz instruments if we look at the hertz value of the radio frequency. So the neighbor here being split, spin up and spin down has equal probability according to quantum mechanics, okay? So when these are observed, okay, that's what we're observing, it sees the splitting from the adjacent neighbor here. And how many neighbors is this? It's the n+1 rule. We have what? The one neighbor, okay, 1 + 1. So how do we get to this doublet? That's what we're looking at. But you can already see it, right? The one neighbor has what? It has this splitting up and down. So this signal here gets split, okay? One gets this, what's adding to the magnetic field, and one gets, in effect, subtracting from it. And so instead of showing up as a singlet, it'll show up as a doublet. Okay, there's our doublet. What we actually see then in coupled proton NMR spectra is this splitting pattern, according to the n+1 rule. Okay, are you buying that so far? Just with the spin state. And we didn't have to do the quantum mechanics. No wave equations, no differential equations, no angular momentum, no square root of -1, no hard math. But the idea here, adding to the magnetic field or subtracting from it, gives this difference in the pattern. It's called the multiplicity, Km. It could be a singlet, doublet, triplet, quartet, depending on how many neighbors are observed there. Okay. All right, let's look at the other one here, which will be, we're going to see which one. We're going to observe now this one, which is going to be the one in the triangle, okay? And it's got the 2 neighbors now. How do we get this triplet down here from this? Well, the spin states, right? The 2 neighbors can either be both spin up, okay? Or one can be up and one can be down, okay? So here they're both spin +1, okay? So it's got the 2 neighbors, right? That's affecting the splitting. Or they can both be, what, spin down, okay? Well, is that the triplet? No, the probability of having both of them opposite here, down and then up, there's 2 ways to do that, right? So it's a probability thing. You can have both up or both down, or there's 2 ways to have one up, one down, which keeps the frequency right at the original point, shift-wise. And so what does it result in? The splitting looks like this, okay? And actually the height of what's observed is important. The triplet will have the inner line twice as high as these 2 outer lines. And that's a true triplet. It comes out of the quantum mechanics. of the spin states of the neighbors, right? These are the neighbors, okay? And there's two of them. So we have spin states here, both plus 1/2. I'm not going to do the whole thing here, but there's two ways to do this one plus, this one minus, this one minus, this one plus, and then both of them minus, which is pretty amazing. In fact, NMR is an exact quantum mechanical calculation. Unlike all other quantum mechanics applied to molecules, NMR is one of the few that's actually perfectly exact. And that's what we see. We see a triplet. And this J value should say something about this distance right here is the J, which is about 7 hertz. And same thing here, the same J value. For acyclic compounds, the scalar coupling or the vicinal coupling, as this is usually about 7 hertz. Okay. So yeah, we can relate this to the ethanol example. Questions on this so far? Okay, we'll look at that spectra in a minute and go through that. Let's do the one with ethanol. And that's the one from before, right? And what was the splitting pattern there? And we can assign some shifts here to this already too. So these two here, 2H, will show up at about 3.5 delta. And what will be the multiplicity? How many neighbors do they have? They have 3. So 3 plus 1, so it'll be what? Quartet. Okay. And what about this one here? 2 neighbors. It'll be about 2, or a little over 2 maybe. 2, or 3H, sorry. And what's the multiplicity? It'll be a triplet. So you can do the same analysis there to figure it out. What about the quartet? Let's see, do we need to do the quartet? How do we get the quartet with the 3 neighbors? Here's our regular thing. And how do we do this? Well, there's the 3 neighbors now. And what? 3 up would be one way to do it. And then you got 2 up, 1 down. This one up, this one down, this one up, and then we've got this one down, and these 2 up. So it's 3 ways to have 2 up, 1 down, okay, with the 3 spin states. And then how do we get the 2 down, 1 up? There's this one up, down, and then this one up, and these 2 down. Yeah, and there's 3 ways to do that, and there's only one way to have them all 3 down. So the quartet will look like this. Or actually, these lines here, I should do that a little bit better. These lines here in the interior are actually 3 times as big as the ones on the side. But that's how a true quartet would look. And don't worry about that. You can go through the probabilities and see how you array the different spin states. You have to have 2 up here and 1 down for this one. And what? 2 down, 1 up for this one, and then all 3 down there. Okay. Anyway, you buying this so far? Believe it or not, this is quantum mechanics, and it's a practical part of it. Let's go back to the overheads and see here what we just looked at. There's the one we just did. Yeah, doublet for 2 hydrogens. These are right here at 4. Okay. And then here's our triplet down here at 5.7. And that's for this 1 hydrogen with the 2 neighbors. Okay. And so that pattern there lets us know, and especially combined with mass spec, we'd be able to nail that down quite easily, the molecular weight, and then figure out what that pattern is with the doublet and the triplet. Okay, so there's your n+1 rule. You should be familiar with that. Here are the common patterns that you'll see over and over again in different molecules. So coupling patterns, by the way, when they're coupled to each other, they'll have the same J value. Okay, that's 7. If it's a little bit higher, 9, you'll see the 9 and the 9 showing up in the other coupling partner. If it's a little bit lower, 5 and 5, you'll see that same J value. That's a way to tell what's coupled to what. We'll show you with 2D NMR how you can determine that a little better. But here's your ethyl fragment that we saw in ethanol. That's that quartet triplet thing. And if you have a methyl next door to a methine, then you got a quartet doublet kind of thing. You can kind of see those patterns. And the other ones to keep in mind are what? The tert-butyl, which is just one big singlet, okay, all 9 hydrogens the same. And isopropyl, where you have a doublet and a small little hairy guy, a heptet, okay. So here's another one to put on that chart, I think. Big doublet that integrates for what? 6 hydrogens here. It's further upfield, okay? And further downfield, closer to whatever group's on the isopropyl. This is an isopropyl group, right? This one has how many neighbors? So it can be in multiple groups. It doesn't have to be on just one carbon. These are equivalent neighbors, and how many do we have with 2 methyl groups nearby? 6, right? So it's 6 plus 1 for the multiplicity rule. Number of neighbors is 6, so what? 7 should be the pattern. And here you see it. That would be kind of hard to do, to draw out all the spin states. I won't make you do that, okay? Just know the n plus 1 rule and roughly what we're trying to do there. But you can see how it works, right? 7 little lines. The outer ones are very small. Sometimes you don't see them. But there are 7 lines here in this pattern, a heptet for this methine hydrogen right here. The 2 methyls are the same. So that's just one set. The methine's a distinct set, so 2 for the isopropyl there. This is more complicated, okay? Propyl, just when you think you got this figured out, right? What are we going to see here? Well, we've got this. We've got this one here, alpha to the bromide. That's okay, right? Because it just has one not equivalent set neighbor. This methylene, right? So that should be, right here, HC should be what? A triplet, right? And HA, these 3 hydrogens here in the methyl group should be okay because they just have the methylene neighbor. So that should be a triplet too. Do you see the 2 triplets here? Yeah, okay. This one at 1 and this one at 3.4. Okay, 2 triplets. This one integrates for 2. This one integrates for 3. The integral's not on there, but we'd give you those numbers sometimes to help you out. Do you see why 1 is shifted at 3.4 and 1's down at 1? That's something to review real quick. Which is which again? The one at 3.4 is what? Alpha to the bromide, right? Because that's an electronegative atom, so it's shifted further downfield. And then this one up here is more what? Shielded, because it's just next to alkyl stuff. The heteroatom, the electronegative group, is quite remote from the terminal methyl. Terminal methyls are almost always down here around 1, okay? Then you can tell how many neighbors they have. If you see a triplet, you do the minus rule, right? Take away 1 for the multiplicity, it must have what? 2 neighbors, okay? So yeah, that n plus 1 rule works both ways. To see the multiplicity, we add the 1 to the neighbors. To know how many hydrogens we have, you take it away, okay? See how that works? And then what about HB? That's the tricky one. Sextet or hextet, 6-line pattern. Take away 1, how many neighbors must it have? 5, and there you see them. The 3 there and the 2 there. Now, this is a convenient one to start with because the J value, the couplings on both sides here are almost equivalent. And so this is really what we'd call an apparent sextet or an apparent hextet. Because in theory, these J values are different. And this is a complex splitting pattern now because it has 2 neighbors that are non-equivalent. And that's where things can get complicated. We'll need to go to the board and analyze this a little bit, Jesher, and let's look at this. So we've got this propyl bromide. So let's analyze this, and we'll just look at the middle carbon there. Just look at that, and it's showing up as a hextet right now, okay, a 6-line pattern with the 5 neighbors. And that's okay for most analysis, but let's back up a little bit because this J value might be different here from this one here, okay? The J couplings might be a little different. In fact, if we looked at this J value here, this might be a triplet, okay, for coupled to the methylene. And what would it be over here? It would be a quartet coupled to the methyl. It might show up as a triplet of quartets, okay? And that's a complex pattern that can be a little bit tricky to figure out. When it's complex, okay, we mean it has multiple coupling partners, okay? and it's the n+1 times the m+1 rule, where this is the one non-equivalent set it's coupled to, and this is the other one here. So what, 2 partners to the methylene, so this is a triplet, and this one over here has 3, and this is the quartet. Okay. Doublet of doublets are very common if there's 2 methynes next to each other. If there's a methylene and a methyne, a doublet of triplets is common. So we're kind of going to a more complicated one here. A what? A triplet of quartets. So let me show you how to do this. Okay, do the large J first. Okay, and the large J is this triplet, let's just say. Okay. There's our triplet, and let's just say, for the sake of argument, it's large. It's 20 hertz, so it's going to spread things out nicely. Okay, so that's quantum mechanically looking at the spin state of what the methylene next door. Okay, it'll split out to a triplet. And then what's the next one we got to do? Oh, quartet. Ouch. So how many lines here? And these are going to be small. Let's say that the quartet here, the J is 3 hertz. And we see this sometimes. We're getting you ready for a harder example where we'll see these multiplets of multiplets, okay? And this lets you do it, come at it a little easier, I think. Okay, and then this line will be split as a quartet, and then this line will be split as a quartet also, okay? So how many lines will you observe? If you had a large one and a small one, you could see what? 12 lines, okay, from a triplet of quartets, okay? You don't see this here. You see what? A hextet, sextet, okay? 6-line pattern. How do we go from 12 lines? That would be the theory if we had one large coupling and one smaller coupling. What if we had where they were both the same? So let's do both J and J prime equal to 7. What would we see? Now this is a little harder to draw, so hopefully I'm doing this all right. Some of you will probably do this a lot better than me. Okay, so let's do the quartet first. Okay. They're both the same. You can do the triplet or the quartet first, doesn't matter. I like to do the highest multiplicity first when they're equal, because then I have to line up the lines here for the triplet. So that was our quartet. Now let's do the triplet. So each one of these has to be split in 3. And this one reaches over and has the same magnitude. See, there's the J, 7, and here's the J7 also, hertz, right? Did I do that right? So this line is now coincidental with that line. And notice this middle line here is coincidental with that line. We got to reduce the number of lines from 12 to 6, right? It's a lot easier to do it qualitatively than quantum mechanically. You can plug these into really complex equations and get this too when you have the same hertz value. But let's see. So this one here will also split out. And let's see if I get this right. Yep. Okay. Got it right. And then this one here. Yep. Got that right. Yep. Okay. So we did 2 more. And then this one here. Yep. Okay. That would be there. And that would be there. That would be there. How many lines do we see in the end? 6. There it is. 6 lines. Okay. Now, why do I call it an apparent hextet or an apparent sextet? It's because the couplings are the same or very similar. Okay. It won't show up as a true hextet, but because these lines are coincidental, the n+1, m+1 here, where they're both the same magnitude, you don't see 12 lines, okay, like you would get if you did this, right? This would be what? 3 times 4, right? That would be 12 lines. There they are, okay? If they had different enough J values, you would see them, but not if they're coincidental in the same value, okay? Does that make sense? So a lot of times you can just say, oh, 6. Well, how many neighbors did it have? 3, 2. Yeah, that should be a hextet. Okay. It's okay. And most of the times that'll be true, but not always. So let's see. Questions on this one? Okay, so we analyze that. Okay. All right. Let's do this one now. This one's a little more complicated. And this one, you'll see these multiple patterns now. And it's a relatively simple molecule, right? It's just vinyl acetate. It's got these structures here. And how many signals do we have? How many non-equivalent sets? That's the first thing to look at, right? This hydrogen here is different than that one. So you got two there. How about this HB? Yeah, that's different than HC because this one's trans to the acetate and this one's cis to the acetate. Okay. And then this methyl here is obviously different. So how many total sets? 1, 2, 3, 4. And there you see them all. 1, 2, 3, 4. This one's a singlet. You should see why. There's no neighbors, right? And it's alpha to the carbonyl on this side. So yeah, it's around 2, 2.5. Okay. Integrates for 3. And then you have 3, what? Alkene region ones. This one right here, HD, is way up here. Why? Because it's on an alkene and it's alpha to this oxygen. Okay, that's an electronegative group. So this HD is way up here around 7. It's in the aromatic range. It's not an aromatic molecule though. Each of these signals integrates for 1 hydrogen. But look at this one. It's a doublet of doublets. Okay, looking at this HD, it's coupled to HC as a doublet, as a Hertz value, and it's coupled to HB with Hertz value. HD to B is a trans coupling. That can be up to 20 Hertz. And in fact, this one you see, this large coupling. And the 20 Hertz value is right here, from this line here on the outside to this line 2 over in the interior. That distance right there is 20 Hertz. And then it's coupled to C here, which is about 10 Hertz. And that's the smaller coupling right here. Okay. You also see this large coupling right here in HB because you still have the 20 Hertz J value. And then the smaller geminal coupling, we call it. This is a J2 coupling. It's 2 bonds away. So the neighbor is distinct even though they're on the same carbon. And you see that with alkenes quite a bit. They make alkenes complicated. HC to HB right here, you see a small J value, and that's like 3 Hertz right there. And then HC, you see the smaller cis coupling to D, and then you see the same small geminal coupling to B. Okay, we'll diagram that out on the board, but what I'd like to do now is actually work a couple problems with you and see if you can come up with what the spectra would look like. So we'll go back to that hard one on Monday and review that, but right now let's look at these. So come up, let's practice. What would the spectrum look like for that? What would it look like for this? And this? And this? And this? See if you can assign what the shifts might be. It might be approximate. You might want to have the shift table in front of you. So if you're watching the video, you might want to pause it and try to work through these. Not you, Joshuan, leave it going. Okay. But yeah, in class here, we can start to go through these kind of quick. But yeah, if you watch the video later, you can pause it and work through it and see how it goes. So how about this? This 1,2-dibromoethane. How many sets? That's always the first thing to look at. 2? 2 sets? Anybody want to offer something else? Is this methylene the same as that methylene? Is there a symmetry operation? Yeah, they're the same. So 1 set. Okay. It'll be a singlet, and it'll be a delta of about 3 ppm. And how many hydrogens under that signal? Well, you can't really tell. Okay, you'd need the molecular formula or mass spec to figure it out. But that would be pretty easy, right? It just look like that. Okay. No coupling. Okay. It doesn't couple to anything that's equivalent. Okay. Some beginning students say, well, that methylene sees these two. It should be a triplet. No, that's resonating same spot as that simultaneously. There's no coupling. It's not perturbing the spin states at all. Okay. Stays right as a singlet. How about this one, though? How many non-equivalent sets here? Bromo ethanol. Anybody? How many sets? 2. Okay. These 2 certainly, but don't forget about that. Is that a different hydrogen? Yeah. So how many total? 3 here. This one can be variable, and it'll be a singlet, and it'll be kind of broad and kind of blobby. okay? And we don't have any coupling here, even though this is next door to this methylene because of the hydrogen bond exchanges, no coupling, no J value for the hydrogen. But it is a distinct set, so we have 3 here. This one will be about 3.5. This one here will also be around 3.5 because it's next door to that. So they might be kind of close to each other, these two here. But these are different sets. So what will be the splitting pattern here? 2 neighbors. This will certainly be a triplet, okay? And then a triplet here also, integrating for 2. So you'd see a triplet and then a real triplet nearby. You have to differentiate between those two. And then somewhere it would be this blobby thing integrating for 1, okay? And when you do quiz 8, I think you've got to come up with a spectrum for a compound. And approximately, you can have the shifts approximate, but use the table to come up with where you think they'll actually be. If you have them way off, then we might mark off some points, but make sure you have the multiplicity correct and the position, okay? So 0, you know, you don't have to show TMS, but it's always normalized to the shift to TMS, okay? So don't call TMS another group, okay? It's a signal that will show up in the NMR often, but that's what we calibrate the instrument to. We put that as the 0 frequency, okay? But yeah, 2 triplets and a singlet there for this guy. Okay, how about this one? How many sets here for this ketone? 3, very good. And where will they be? Maybe 2.1 here. This one about 2.5, and this one down here around 1, okay? So kind of see where they're going to be, and then combined with the IR data, that would really help you out. What about multiplicities here for this one? How many neighbors? 0. So what will it be? Singlet. Okay, yeah, use the terminology. How about this methylene right here? How many neighbors? So it will show up as a quartet. Okay, and how about this guy? How many neighbors? 2. It'll be a triplet. Okay, so I think you could draw that pretty good, right? Your 2.5 would be where you want your quartet. So, you know, your scale, make sure you draw that there. Oh, and then around 2 here, you got to have your singlet. Okay. And then down here around 1, you got to have what? Your triplet. And that'll be a little bit bigger. That'll integrate what? 2 to 2 to 3. Okay. Yeah. Okay. So that's a powerful thing. We're connecting the structure to the spectra, right? And then we're looking at spectra and coming up with structure. So it goes both ways. So that's why I think it's good to emphasize this. What would these simple molecules really look like in the proton NMR? Okay. And if you get used to seeing that in the other direction, it'll become easier for you. Okay, what about this one? This is going to be more complicated. How many sets here? Count them up. 1, 2, 3. Is this one different? Yeah. 4, 5 sets, right? And let's see, can we figure this out? This one will be variable, it'll be a singlet. This one here, alpha to the alkene, de-shields it a little bit, but alpha to this oxygen a lot. I'd say that would be around 4, okay? But look, it has no neighbors. There's nothing else on the carbon here. So what will it show up as? A singlet, okay? So we already have quite a bit of information there. What about this one here? These two will be kind of hard to tell, you know, where they'll be. They'll both be around 5. You can call one of them maybe 5.2 and one 5.3. And what will be their multiplicities? They are a distinct set. They're not equivalent. So they are coupled to each other, okay? But there's nothing on this one. There's a methyl here, right? So they'll both be doublets, okay? And that's kind of cool. You'll see them resolved, especially if you have a high field instrument. And what about this one? Again, no neighbors, singlet. It'll be about 2.5. It's alpha to the alkene. So it's not right at 1. It's shifted a little bit further down. So, but this would be a singlet also. But I think you could draw that out too and have a good representation of what that might look like. Okay. Questions on this exercise? Was this helpful to go through this and see this? And you can do that. And there's some problems, of course, in the book to do that. But we'll do this next time. We'll go through and analyze these splitting patterns. Actually, good graphics in your book for this harder one here. And again, this is a complex system with multiple spin system couplings. So we have to use the n+1 times m+1 rule to figure this out. The magnitudes of the couplings are different. The trans one, here it is, 14. That can be all the way up to 20. Okay, that's the large one right here. And you see it right there. That's the 14. And then you've got the cis one, which is also pretty large. That's right here, 6.5. Okay, and you see it over here. Okay. And then the small one is the geminal coupling right here, the J2 coupling, which is C to B, and that's the small one right here. What is it? Oh, it's 1.2. Sometimes they're very small. They don't show up. They'll show up as a singlet, especially if you have a lower field instrument there. But that pattern, we might leave it at that. This example goes back to chapter 13, and maybe we'll pick it up here next time. But yeah, the whole thing on Monday will be solving a lot of things. So read up through the end of chapter 14, and we'll show you a lot more spectra, and it will help you solve problems in the other direction, where you're given a bunch of data and you got to come up with a structure. Okay. Have a good Thanksgiving. We'll see you then. Oh, we also have. We'll do office hours today at 1 if you want to zoom in with questions. Okay, very good. We'll see you next week. Okay.